This is video number 6 that's introducing my new books and chart that's been available that I've mentioned in previous videos. It's October 30th. I'm making this video today as well because I need to include more about surface gravity. Surface gravity, I mentioned in the previous video that it's reciprocal. And okay, so what's being implied is that if an object over Mars drops more slowly toward its surface than the same object would drop over Earth's surface, irrespective of, we're not talking about atmosphere affecting feathers or anything like that here. Okay? The Earth's atmosphere it offers some resistance to falling objects. Yes, it does. And Mars' atmosphere is very wispy. Okay. True. But still, that has no bearing on what I'm trying to explain here. That should be as easy to understand for anyone that thinks this through as understanding the simplest math problem you can imagine. To me, it seems like that. When you drop a body or an object, let's say an object of 1 kilogram, 2 pounds roughly, over the Earth, it drops at roughly 9.8 or roughly 10 meters per second squared. Over Venus, it falls roughly 9 meters per second squared because Venus has less mass than the Earth. Therefore, it exerts less gravitational force on that 1 kilogram object. On Mars, it falls even much more slowly. Its acceleration rate is even much more slow. It's much less. The 1 kilogram object would fall at 3.7 meters per second squared. Okay, now let's turn that around and let's say, since gravity is reciprocal, Mars and that object, okay, they're actually exerting an attraction force that's causing them one to fall toward the other, okay? But, you know, if you increased the mass of this 1 kilogram object to the mass of something like the Earth, let's say, and put it next to Mars, now which one would fall toward the other one? Okay, now if orbits, by the way, don't always occur. Sometimes a body is headed directly toward another body with a lot of mass. Often some that are very much more massive. And those, they might not be headed exactly toward it, but they might be headed just a little bit off, and then they curve and they intersect it. Okay, that happens sometimes. Or maybe they're going directly at it and they intersect it, and so there's a collision. Okay, it's the bodies that are not headed directly at another one that could become its primary that it orbits. They're going by and they get caught by their gravitational force that's pulling on them, and that turns them. But it doesn't turn them enough to make an intersection with them. This is what causes orbits. There's no warped space or anything like that that's causing orbits. The Lorentz Transition, we don't need that. That's not needed. It's not explaining what really how nature really works. Okay, all of that, you know, Einstein came along, came up with general relativity and special relativity and all this different, you know, that time doesn't elapse at the same rate everywhere, gravity affects it. And so and then the space is warped because these bodies are not being pulled or tethered by gravity, and it's a compromise between their forward momentum that wants to continue in a straight line being turned into angular momentum that circles the body. And now they say space is causing it to turn. Okay, that's not what's happening. When you put a body the size, the mass of the Earth next to the mass of Mars, now instead of a 1 kilogram object, you have the Earth fairly close to Mars. And if they're not, they don't have any motion that is not directly, you know, that is, if one of them has a lot of motion in a different direction from heading toward one another, then you're going to get an orbit. But if let's just say there's no motion involved relative to the two bodies. Formerly you had a 1 kilogram mass that would fall at 3.7 meters per second squared toward Mars. Now you've got the Earth basically right there. And so instead of this, but you have two bodies reciprocating gravity. This essentially, it's the same thing in principle. And so when you have the Earth replacing the 1 kilogram object next to Mars, you're going to have Mars falling toward the Earth. Now you'll have the Earth Mars is large enough, the Earth would probably move toward, if they don't have other motion off in another direction that has to be factored in with all of this. If they're just sitting there next to one another and they're going to be able to collide simply by their gravity, okay, gravitational force, then it's no longer that this body that used to be 1 kilogram in the place of the Earth is falling at 3.72 meters per second squared. It's the Earth is going to move toward Mars a little bit, and Mars is going to respond more because it has less mass and therefore it has less inertia to get it going and get it moving. And so it's going to be attracted to the Earth, and it's going to fall at some 10 meters per second squared toward the Earth. Now it might even be greater than that because you've got two very large, massive bodies which would have a change, which would result in a change and probably the surface gravity involved when you have bodies that close that are about to collide. This is, let me go ahead and explain this too. I have a long hill next to the location where I live, and on this highway, I-635, it's nearly a mile long, it's steep, and I have a lot of weight in my van, parts and tools. It's really loaded heavy for the size of the van, and I'm routinely coming down that hill toward my house on this highway, and I have other vehicles next to me that are also going down the hill. No one accelerates on that hill because you're already approaching 70 miles per hour if you just go 65 or whatever over the crest of the hill, and then you coast, you're going to go about 70 miles an hour per hour down that hill, regardless. And the thing is, if relativity was correct, and there's an empty car in front of me, or on various days, and except for the driver, and I have all this weight in my van, invariably, no one steps on their brake unless they have to. So you can see the brake lights if the brake is applied. No one is accelerating because you'd be going too fast. So everybody's coasting down that hill. I'm coasting, and there's a certain amount of distance between me and the car ahead of me. And invariably, I pull closer and closer to it. Sometimes I have to go around it because of that. This happens every day, almost every day. Okay, that contradicts relativity's equivalence principle. Just as well as when you drop two very mass bodies that are the same surface, smooth surface, and they're the same size, in two tubes of water where you have no interference from currents of the water. You drop those simultaneously, and the slightly heavier one, they're experiencing the same resistance, and the heavier one reaches the bottom quicker. That debunks relativity's equivalence principle.